ये है इक्विलिब्रियम, जिसमें सिर्फ हम केमिकल इक्विलिब्रियम वाला पार्ट ही देख रहे हैं यहाँ पर अभी। तो इसमें देखेंगे कि आफ्टर स्टडिंग दिस यूनिट identify the dynamic nature of the equilibrium involved in the physical and the chemical processes. State the law of the equilibrium, explain the characteristic of the equilibrium involved in the physical and the chemical processes. Write the expression for the equilibrium constant. Establish a relationship between the Kp and the Kc. ऐसे Kp इज इक्वल टू हो जाता है Kc, Kp इज इक्वल टू हो जाता है क्या, तो Kp इज इक्वल टू हो जाता है Kc RT डेल्टा Ng, ये हो जाता है। और एक्सप्लेन वेरियस फैक्टर्स दैट अफेक्ट द इक्विलिब्रियम स्टेट ऑफ ए रिएक्शन। क्लासिफाई सब ठीक है, बस यहाँ तक ही है जो देख रहे हैं, इस यही पार्ट तक है जो देखेंगे, क्योंकि नेक्स्ट आगे वाला जो पार्ट आता है वो है आयोनिक इक्विलिब्रियम का, तो उसको है जो अगले पार्ट में देखेंगे। तो एनसीईआरटी कहता है केमिकल इक्विलिब्रियम आर इम्पॉर्टेंट इन न्यूमरस बायोलॉजिकल एंड इन्वायरमेंटल प्रोसेसेज। फॉर एग्जांपल इक्विलिब्रिया इन्वॉल्विंग द O2 molecules and the protein hemoglobin play a crucial role in the transport and the delivery of the O2 from our lungs to our muscles. Similar equilibria involve CO molecules and the hemoglobin account for the toxicity of the CO. When a liquid evaporates in a closed container, molecule with a relatively higher kinetic energy escape the liquid surface into the vapor phase, and the number of the liquid molecules from the vapor phase strike the liquid surface and are retained in the liquid phase. It gives rise to a constant vapor pressure because of an equilibrium in which the number of the molecules leaving the liquid equals the number returning to the liquid from the vapor. We said that the system has reached equilibrium state. At this stage, however, there is not a static equilibrium and there is a lot of the activity at the boundary between the liquid and the vapor. Thus, at equilibrium, the rate of the evaporation is equal to the rate of the condensation. It may be represented by H2 लिक्विड से H2 है जो वेपर में जा रहे हैं। The double half arrow indicate that the process in both the direction are going simultaneously. The mixture of the reactants and the products in the equilibrium is called as the equilibrium mixture. आगे इंसर्ट बोलते हैं कि equilibrium can be established for both physical process and the chemical reactions. The reaction may be fast or the slow depending upon the experimental condition and the nature of the reactants. When the reactants in a closed vessel at a particular temperature react to give the products, the concentration of the reactants keep on decreasing, while those of the products keep on increasing for some time, after which there is no change in the concentration of either of the reactants or products. This stage of the system is the dynamic equilibrium, and the rate of the forward and the reverse reaction become equal. It is due to this dynamic equilibrium stage that there is no change in the concentration of the various species in the reaction mixture based on the extent to which the reaction proceeds to reach the state of the chemical equilibrium. These may be classified in the three groups. पहला the reaction that proceed nearly to the completion on only negligible concentration of the reactants are left. In some cases it may not be even possible to detect these experimentally. और दूसरा the reaction in which only a small amount of the products are formed and most of the reactants remain unchanged at the equilibrium stage. और तीसरा the reaction in which the concentration of the reactants and the products are comparable when the system is in the equilibrium. The extent of the reaction in the equilibrium vary with the experimental conditions such as the concentration of the reactants, temperature, etc. Optimization of the operational condition is very important in the industry and the laboratory, so that equilibrium is favorable in the direction of the desired product. Some important aspects of the equilibrium involving physical and the chemical processes are dealt in this unit, along with the equilibrium involving ions in the aqueous solution, which is called as the ionic equilibrium. अब देख रहे हैं इक्विलिब्रियम इन द फिजिकल प्रोसेसेस, तो बोल रहा है द कैरेक्टरिस्टिक ऑफ द सिस्टम एट इक्विलिब्रियम आर बेटर अंडरस्टूड इफ वी एग्जामिन सम फिजिकल प्रोसेसेज. द मोस्ट फैमिलियर एग्जाम्पल्स आर द फेज ट्रांसफॉर्मेशन प्रोसेस. एग्जाम्पल सॉलिड से लिक्विड में जा रहे हैं, लिक्विड से गैस में जा रहे हैं और सॉलिड से गैस में जा रहे हैं, वो हो जाएगा. The solid liquid equilibrium तो कहता है कि ice and the water kept in the perfectly insulated thermos flask, no exchange of the heat between its content and the surrounding at 223 Kelvin, and the atmospheric pressure are in the equilibrium state, and the system shows interesting characteristic features. We observe that the mass of the ice and the water do not change with the time and the temperature remains constant. However, the equilibrium is not static. The intense activity can be noticed at the boundary between the ice and the water. Molecules from the liquid water collide against ice and adhere to it, and some molecules of the ice escape into the liquid phase. There is no change of the mass of the ice on the water at the rate of the transfer of the molecule from the ice into the water and of the reverse transfer from the water into ice are equal at the atmospheric pressure and the 273 Kelvin. It is obvious that ice and water are in the equilibrium only at a particular temperature and pressure. For any pure substance at the atmospheric pressure, the temperature at which the solid and the liquid phase are at the equilibrium is called the normal melting point or the normal freezing point of the substance. The system here is in dynamic equilibrium and we can infer the following. Both the opposing processes occur simultaneously. दूसरा, both the processes occur at the same rate so that the amount of the ice in the water remains the constant. अब आता है लिक्विड वेपर इक्विलिब्रियम. तो कहता है कि दिस इक्विलिब्रियम कैन बी बेटर अंडरस्टूड इफ वी कंसीडर द एग्जांपल ऑफ a transparent box carrying the U2 with the mercury manometer. Drying agent like the anhydrous calcium chloride or the phosphorus pentoxide is placed for a few hours in the box. After removing the drying agent by tilting the box on one side, a batch glass or the petri dish containing water is quickly placed inside the box. It will be observed that the mercury level in the right limb of the manometer slowly increases and finally attains a constant value. That is, the pressure inside the box increases and reaches a constant value. Also, the volume of the water in the batch glass decreases. Initially, there was no water vapor or very less inside the box. As the water evaporated in the pressure in the box increased due to the addition of the water molecule into the gaseous phase inside the box. The rate of the evaporation is constant. However, the rate of the increase in the pressure decreases with the time due to the condensation of the vapor into the water. Finally, it leads to an equilibrium condition when there is no net evaporation. This implies that the number of the water molecules from the gaseous state into the liquid state also increases till the equilibrium is attained. That means rate of the evaporation is equal to rate of the condensation. At equilibrium, the pressure exerted by the water molecule at a given temperature remains constant and is called as the equilibrium vapor pressure of the water or just the vapor pressure of the water. Vapor pressure of the water increases with the temperature. If the above experiment is repeated with the methyl alcohol, acetone and the ether, it will observe that different liquids have the different equilibrium vapor pressure and at the same temperature, and that the liquid which has a higher vapor pressure is more volatile and had a lower boiling point. I कहता है कि if we expose 3 batch glasses containing separately 1 ml each of the acetone, ethyl alcohol and the water to the atmosphere and repeat the experiment with the different volume of the liquids in a warmer room, it is observed that in all such cases the liquid eventually disappear and the time taken for complete evaporation depends upon the nature of the liquid and the amount of the liquid and the temperature. When the watch glass is open to the atmosphere, the rate of the evaporation remains constant, but the molecules are dispersed into large volume of the room. As a consequence, the rate of the condensation from vapor to the liquid state is much less than the rate of the evaporation. These are the open system and it is not possible to reach equilibrium in an open system. Water and the water vapor are in the equilibrium position at the atmospheric pressure 1.013 bar and at 4 degrees Celsius in a closed vessel. The boiling point of the water is 4 degrees Celsius at 1.013 bar pressure. For any pure liquid at 1 atmospheric pressure 1.013 bar, the temperature at which the liquid and the vapor are at equilibrium is called as the normal boiling point of the liquid. Boiling point of the liquid depends upon the atmospheric pressure. It depends upon the altitude of the place. At high altitude the boiling point है जो decrease करता है. Solid vapor equilibrium तो कहता है let us now consider the system where solids sublime to the vapor phase. If we place the solid iodine in a closed vessel, after some time the vessel gets filled up with the violet vapor and the intensity of the color increases with time. After a certain time the intensity of the color becomes constant and at this stage equilibrium is attained. Hence solid iodine sublimes to give the iodine vapor and the iodine vapor condenses to give the solid iodine. The equilibrium can be represented as I2 solid से I2 vapor में जा रहे हैं. Other examples showing this kind of the equilibrium are कैंपर सॉलिड से जा रहे हैं कैंपर वेपर और NH4 सॉलिड से जा रहे हैं NH4 वेपर में. अब बात करते हैं इक्विलिब्रियम इन्वॉल्विंग द डिसोल्यूशन ऑफ द सॉलिड्स ऑफ द गैसेज इन द लिक्विड्स. तो सॉलिड्स इन द लिक्विड्स वी नो फ्रॉम आवर एक्सपीरियंस दैट वी कैन डिसॉल्व ओनली ए लिमिटेड अमाउंट ऑफ द सॉल्ट और sugar in the given amount of the water at the room temperature. If we make a thick sugar syrup solution by dissolving sugar at the higher temperature, sugar crystals separate out. If we cool the syrup to the room temperature, we call it a saturated solution when no more of the solute can be dissolved in it at a given temperature. The concentration of the solute in a saturated solution depends upon the temperature. In a saturated solution, a dynamic equilibrium exists between the solute molecule in the solid state and in the solution. Sugar solution is sugar solid, and the rate of the dissolution of the sugar is equal to rate of the crystallization of the sugar. Equality of the two rate and the dynamic nature of the equilibrium has been confirmed with the help of the radioactive sugar. If we drop some radioactive sugar into the saturated solution of the non-radioactive sugar, then after some time radioactivity is observed in both in the solution and in the solid sugar. Initially there were no radioactive sugar molecule in the solution, but due to the dynamic nature of the equilibrium there is a exchange between the radioactive and the non-radioactive sugar molecule between the two phases. The ratio of the radioactive to the non-radioactive molecule in the solution increases till it remains a constant value. Next, gas phase in the liquid. तो कहता है when a soda water bottle is opened, some of the carbon dioxide gas dissolve in it, fizzes out rapidly. The phenomena arise due to the difference in the solubility of the carbon dioxide at a different pressure. There is equilibrium between the molecules of the gaseous state and the molecules dissolved in the liquid under the pressure. That means CO2 gas और CO2 in the solution के बीच में equilibrium है. This equilibrium is governed by the Henry law, which states that the mass of a gas dissolved in a given mass of the solvent at any temperature is proportional to the pressure of the gas above the solvent. This amount decreases with the increase of the temperature. The soda water bottle is filled under the pressure of the gas when its solubility in the water is high. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escape to reach a new equilibrium condition required for the lower pressure, namely its partial pressure in the atmosphere. This is how the soda water in the bottle, when left open to the air for some time, turns flat. It can be generalized that for the solid liquid equilibrium there is only one at temperature melting point at 1 atm 1.013 bar at which the two phases can coexist. If there is no exchange of the heat with the surrounding, the mass of the two phases remains constant. दूसरा कि for the liquid vapor equilibrium the vapor phase is constant at a given temperature. और तीसरा for the dissolution of the solids from the liquids the solubility of is the constant at a given temperature. For dissolution of the gas phase in liquids, the concentration of the gas in the liquids is proportional to the pressure concentration of the gas over the liquid. These observations are summarized in the table 6.1. तो सम फ्यूचर ऑफ द फिजिकल इक्विलिब्रियम है कि लिक्विड से वेपर H2O से H2O जा रहे हैं. तो कंक्लूजन PH2O कांस्टेंट, PH2O जो है कांस्टेंट एट ए गिवन टेम्परेचर पर. फिर सॉलिड से लिक्विड जा रहे हैं H2O सॉलिड से H2O लिक्विड, तो मेल्टिंग पॉइंट इज फिक्स्ड एट ए कांस्टेंट प्रेशर पर. फिर सॉल्यूट सॉलिड से सॉल्यूशन जा रहे हैं तो कॉन्सेंट्रेशन ऑफ द सॉल्यूट इन द सॉल्यूशन इज कांस्टेंट एट ए गिवन टेम्परेचर पर. शुगर से शुगर सॉल्यूशन जा रहे हैं और फिर गैस से गैस जा रहे हैं तो गैस इज कांस्टेंट एट ए गिवन टेम्परेचर पर. फिर CO2 गैस और CO2 एक्वस जा रहे हैं तो CO2 एक्वस CO2 गैस इज कांस्टेंट एट ए गिवन टेम्परेचर. अब बात करते हैं जनरल कैरेक्टरिस्टिक ऑफ द इक्विलिब्रियम इन्वॉल्विंग द फिजिकल प्रोसेसेस. तो बोलता है कि फॉर द फिजिकल प्रोसेसेस डिस्कस्ड एबव फॉलोइंग कैरेक्टरिस्टिक आर कॉमन टू द सिस्टम एट इक्विलिब्रियम. पहला कि इक्विलिब्रियम इज पॉसिबल ओनली इन ए क्लोज्ड सिस्टम एट ए गिवन टेम्परेचर. बोथ द अपोजिंग फोर्स ऑकरिंग एट द सेम रेट एंड देयर इज डायनामिक बट स्टेबल कंडीशन or all measurable property of the system remain constant. Next, when the equilibrium is attained for a physical process, it is characterized by the constant value for one of its parameter at a given temperature. Table 6.1 lists such quantities. और अगला है कि the magnitude of such quantity at any stage indicates the extent to which the physical process has proceeded before reaching the equilibrium. Next है equilibrium in the chemical process, dynamic equilibrium. तो analogous to the physical system, chemical reaction also attain a stable state of the equilibrium. These reactions can occur both in the forward and the backward direction. When the rate of the forward and the reverse reaction become equal, the concentration of the reactants and the products remain constant. This is the stage of the chemical equilibrium. This equilibrium is dynamic in the nature as it consists of a forward reaction in which the reactant gives the product and a reverse reaction in which the product gives the original reactant. For a better comprehension, let us consider a general case of the reversible reaction. A से B, C से D जा रहे हैं. तो with the passage of time there is accumulation of the product C and D and the depletion of the reactant A and B. This lead to a decrease in the rate of the forward reaction and an increase in the rate of the reverse reaction. तो यहाँ पर है अटेनमेंट ऑफ द केमिकल इक्विलिब्रियम दिखाए हुए है. ये हो गया कॉन्सेंट्रेशन, इधर हो गया इक्विलिब्रिया, ठीक है, ए से बी, और इधर हो गया सी से डी दिखाए हुए. तो आगे कहता है कि इवेंचुअली द टू रिएक्शन ऑकर एट द सेम रेट एंड एट द सिस्टम रीचेज ए स्टेट ऑफ द इक्विलिब्रियम. Similarly, the reaction can reach the state of the equilibrium even if B start with only C and D. That is, no A and B being present initially, as the equilibrium can be reached from the either direction. The dynamic nature of the chemical equilibrium can be demonstrated in the synthesis of the ammonia by the Haber process. In a series of the experiment, the Haber started with the unknown amounts of the dinitrogen and dihydrogen, maintained at the high temperature and the pressure, and at the regular intervals determined the amount of the ammonia present. He was successful in determining also the concentration of the unreacted dihydrogen and dinitrogen. Figure 6.4 shows that after a certain time the composition of the mixture remains the same even though some of the reactants are still present. This constancy in the composition indicates that the reaction has reached equilibrium. In order to understand the dynamic nature of the reaction, synthesis of the ammonia is carried out with exactly the same starting condition of the partial pressure and the temperature, but using D2 deuterium in place of the H2. This reaction mixture starting either with H2 or D2 reach equilibrium with the same composition except that D2 and the ND3 are present instead of the H2 and the NH3. After कहता है कि after equilibrium is attained, these two mixture H2 N2 NH3 D2 N2 and the NH3 are the mixed together and left for a while. Later, when this mixture is analyzed, it is found that the concentration of the ammonia is just the same as before. However, when this mixture is analyzed by a mass spectrometer, it is found that ammonia and all the deuterium containing form of the ammonia NH3, NH2D, NHD2 and the ND3 are dihydrogen and its deuterated forms H2, HD and D2 are present. Thus one can conclude that scrambling of H and D atoms in the molecules must result from a continuation of the forward and the reverse reaction in the mixture. If the reaction had simply stopped when they reached equilibrium, then there would have been no mixing of the isotope in this P. Use of the isotope deuterium in the formation of the ammonia clearly indicates that the chemical reaction reach a state of the dynamic equilibrium in which the rates of the forward and the reverse reaction are equal and there is no net change in the composition. यहाँ पर दिखाए हुए है डिपिक्शन ऑफ द इक्विलिब्रियम फॉर द रिएक्शन N2 + 3 2NH3 दे रहा है, तो अलग अलग के लिए ग्राफ हो गया, ठीक है, दिए हुए. Next, equilibrium can be attained for both from both sides, whether we start reaction by taking H2 and N2 and get NH3 or by taking NH3 and decomposing it into N2 and H2. तो N2 + 3 H2 भी 2NH3 देता है. Similarly, आगे कहता है कि similarly, let us consider the reaction H2 + I2 2HI. If we start with equal concentration of the H2 and the I2, the reaction proceeds in the forward direction and the concentration of the H2 and the I2 decreases while that of the HI increases until all of these becomes constant at the equilibrium. We can also start with the HI alone and make the reaction to proceed in the reverse direction. The concentration of the HI will decrease and the concentration of the H2 and the I2 will increase until they all become constant when the equilibrium is reached. If total number of the H and I atoms are same in the given volume, the same equilibrium mixture is obtained whether we start it from the pure reactants or the pure products. तो यहाँ पर दिए हुए chemical equilibrium in the reaction H2 + I2 2HI can be attained from the either direction से. अब बात करते हैं law of the chemical equilibrium and the equilibrium constant. तो कहता है कि mixture of the reactants and the products in the equilibrium of state is called as the equilibrium mixture. In the section we will address a number of the important questions about the composition of the equilibrium mixture. What is the relationship between the concentration of the reactants and the products in an equilibrium mixture? How can we determine the equilibrium concentration from the initial concentration? What factors can be exploited to alter the composition of an equilibrium mixture? The last question in particular is important when choosing condition for synthesis of the industrial chemicals such as the H2, NH3, CO, etc. To answer this question, let us consider a general reversible reaction. A plus B देता है C plus D, where A and B are the reactants and C and D are the products in the balanced chemical equation. On the basis of the experimental study of the many reversible reaction, the chemist T.K. Goldberg and the Baje proposed in 1854 that the concentration in an equilibrium mixture are related by the following equilibrium equation कि Kf equal to हो जाता है concentration of the products by concentration of the reactants, where Kf the equilibrium constant and the expression on the right side is called as the equilibrium constant expression. The equilibrium constant is also known as the law of the mass action because in the early days of the chemistry, concentration was called as the active mass. In order to appreciate the work better, let us consider the reaction between the gases H2 and the I2 carried out in a fluid vessel at the fast active scaling per. तो कहता है कि 6 of the experiments with the varying initial condition were performed starting with only gaseous H2 and the I2 in a fluid reaction vessel in first 4 experiment 1, 2, 3 and 4 and only HI in the other 2 experiment 5 and 6. Experiments 1, 2, 3 and 4 were performed taking different concentration of the H2 and or I2. With time it was observed that intensity of the purple color remained constant and equilibrium was attained. Similarly, for experiment 5 and 6, the equilibrium was obtained from the opposite direction. अब कहता है data obtained from all the 6 sets of the experiment are given in the table 6.2. It is evident that from the experiment 1, 2, 3 and 4 the number of the moles of the diiodine reacted equal to number of the moles of the iodine reacted is equal to half number of the moles of the HI format. Also experiment 5 and 6 indicate that H2 is equal to हो जाता है I2 equilibrium पर. So knowing the above facts in order to establish a relationship between the concentration of the reactants and the products, several combinations can be tried. Let us consider the simple expression Hi by Hi2 I2. So it can be seen from the table 6.3 that if we put the equilibrium concentration of the reactants on the products, the above expression is far from the constant. However, if we consider the expression Hi k square by H2 I2, we find that this expression gives the constant value in all the 6 cases. It can be seen that in this expression the power of the concentration for the reactant and the products are actually the stoichiometric coefficient in the equation for the chemical reaction. Thus for the reaction H2 plus I2 2HI, the following equation 6.1, the equilibrium constant Kc is written as Kc is equal to Hi k square by H2 I2. ठीक है, तो generally the subscript EQ it for the equilibrium is omitted from the concentration term. It is taken for granted that the concentration in the expression for the Kc are equilibrium values. We therefore write Kc is equal to Hi k square by H2 I2. The subscript C indicates that Kc is expressed in the concentration of the mole per liter. आगे कहता है कि at a given temperature the product of the concentration of the reaction products raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the product of the concentration of the reactants raised to their individual stoichiometric coefficient has a constant value. This is known as the equilibrium law or the law of the chemical equilibrium. Next है कि the equilibrium constant for a general reaction AA, BB, CC, DD is expressed as Kc. तो CC, DD, AA और BB, where A, B, C and D are the equilibrium concentration of the reactants on the products. Equilibrium constant for the reaction 4Na3 plus 5O2, 4NO plus 6C2 is written as Kc is equal to Na को 4, H2O के 6, Na3 के 4 और O2 के 5. Molar concentration of the different species indicated by enclosing these in the square brackets and I mentioned above. It is implied that these are equilibrium concentration. While writing expression for equilibrium constant, symbol for the phrases F, L and G are generally ignored. फिर कहा जाता है कि let us write the equilibrium constant for the reaction H2 plus I2 2HI as Kf is equal to Hi k square by H2I2 तो X. The equilibrium constant for the reverse reaction 2HI H2 plus I2 at the same temperature is Kf is equal to H2I2 by Hi k square यानी कि 1 by X यानी 1 by Kf हो जाएगा. तो रिएक्शन को पलटने पर Kf है जो 1 by Kf हो जाता है. The equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. और कहता है कि if we change the stoichiometric coefficient in a chemical equation by multiplying throughout by a factor, then we must make sure that the expression for the equilibrium constant also reflects that change. For example, if the reaction 6.5 is written as half H2 plus half I2 is equal to HI, the equilibrium constant for the above reaction is given by K double dash is equal to HI H2 के हाफ I2 के हाफ यानी HI के स्क्वायर इक्वल टू H2 I2 के हाफ, तो x का हाफ यानी Kc का हाफ आ जाएगा। तो ऑन मल्टीप्लाइंग द इक्वेशन 6.5 बाई n we get NH2 प्लस NI2 NH2 NI2 D, तो 2NHI है जो आता है। देयरफॉर द इक्विलिब्रियम कांस्टेंट फॉर द reaction is equal to the Kc Kn. These findings are summarized in the table 6.4. It should be noted that because of the equilibrium constant Kc and the Kc have different numerical values, it is important to specify the form of the balanced chemical equation when quoting the value of the equilibrium constant. अब दिखाता है रिलेशन बिटवीन द इक्विलिब्रियम कांस्टेंट फॉर ए जनरल रिएक्शन एंड इट्स मल्टीपल्स। तो ए बी बी सी सी डी डी, तो के सी जो आता है ये हो गया। फिर अगर रिएक्शन को फ्लैट देते हैं तो के सी 1/K' जो आता है 1/Kc हो जाएगा। और Na एन बी बी एन सी सी डी तो एन डी डी है, तो K' इक्वल टू हो जाएगा Kc के n। ठीक है। अगला क्वेश्चन है कि द फॉलोइंग concentration were obtained for the formation of the Na3 from the N2 and the H2 at equilibrium at the 500 Kelvin। H2 का दिया हुआ है 1.5 गुना 10⁻², H2 का दिया हुआ है 3.0 गुना 10⁻², और Na3 का दिया हुआ 1.2 गुना 10⁻²। तो कैलकुलेट इक्विलिब्रियम कांस्टेंट। तो द इक्विलिब्रियम कांस्टेंट फॉर द रिएक्शन N2 + 3 = 2Na3 कैन बी रिटन एज Na3 के स्क्वायर बाई N2 H2। यहाँ सोल्व करके आ रहा है 1.06 गुना 10⁻3। अगला है कि एट इक्विलिब्रियम द कॉन्सेंट्रेशन ऑफ द N2 3 गुना 10⁻3, O2 4.2 गुना 10⁻3 एंड द NO 2.8 गुना 10⁻3 मोलर इन फ्लूइड वेसल एट 800 केल्विन। तो भाट will Kc for the reaction N2 + O2 2NO। तो फॉर द रिएक्शन इक्विलिब्रियम कांस्टेंट Kc कैन बी रिटन एज NO के स्क्वायर बाई N2O2। तो आ जाएगा 0.622, इसका आंसर आ जाएगा। अब बात करते हैं होमोजीनियस इक्विलिब्रिया की। तो इन अ होमोजीनियस सिस्टम ऑल द रिएक्टेंट्स एंड द प्रोडक्ट्स आर इन द सेम फेज। फॉर एग्जांपल इन द गैसियस रिएक्शन N2 + 3H2 2Na3 reactants and the products are in the homogeneous phase. Similarly for the reaction C3COOH C2H5 aqueous plus H2O liquid, तो ये देता है C3COOH plus C2H5OH and the Fe3 plus Fn minus FeSN2 plus। तो all the reactants and the products are in the homogeneous solution phase. We shall now consider the equilibrium constant for the some homogeneous reaction। पहला है equilibrium constant in the gaseous system। तो कहता है कि so far we have expressed equilibrium constant for the reaction in the terms of the molar concentration of the reactants and the products and use the symbol Kc for it। For reaction involving the gas phase, however, it is usually more convenient to express the equilibrium constant in the terms of the partial pressure। And the ideal gas equation is written as Pv equal to होता है nRT, यानी P equal to होता है n/v/RT, ये हो जाता है। ठीक है। Here P is the partial pressure in the Pascal, n is the number of the moles of the gas, B the volume in the meter cube and T the temperature in the Kelvin। तो कहता है कि therefore n/v is the concentration expressed in the mole per meter cube। If concentration of C is in the mole per liter or the mole per decimeter cube and P is in the bar, then the P is equal to the CRT। तो we can also write P is equal to gas into concentration of gas by RT, जहाँ पर R का वैल्यू आता है 0.0831 बार पर लीटर पर मोल केल्विन। At constant temperature, the pressure of the gas is proportional to its concentration. That means pressure directly proportional to gas होता है। और for reaction in the equilibrium H2 + I2 2HI, we can write either Kc equal to HI के स्क्वायर by H2 I2 और Kc equal to PHI के स्क्वायर by PH2 I2। Further, since PHI equal to HI RT, तो PI2 equal to I2 RT और PH2 equal to concentration of H2 into RT। Therefore Kp equal to PHI के स्क्वायर PH2 by PI2। तो यहाँ से आ जाता है कितना, Kp इक्वल टू आता है Kc। तो कहता है कि इन दिस एग्जाम्पल Kp इक्वल टू Kc, दैट मीन्स बोथ इक्विलिब्रियम कांस्टेंट आर इक्वल। हाउएवर दिस इज नॉट ऑलवेज द केस। फॉर एग्जाम्पल इन द रिएक्शन N2 + 3H2 2NH3 देता है, तो Kp इक्वल टू कितना आता है, Kp इक्वल टू आता है Kc RT⁻²। सिमिलरली फॉर ए जनरल रिएक्शन where delta n जो है नंबर ऑफ द मोल्स ऑफ द gaseous product माने नंबर ऑफ द मोल्स ऑफ द gaseous reactant in the balanced chemical equation, it is necessary that while calculating the value of the Kp, pressure should be expressed in the bar because the standard state for the pressure is 1 bar। We know from the unit 1 that 1 Pascal is equal to आ जाता है 1 Newton meter square and the 1 bar is equal to आता है 10⁵ Pascal। तो Kp values for a few selected reaction at a different temperature are given in table 6.5 है जो दिए हुए हैं। जैसे N2 + 3H2 to 2NH3 और 2FO2 plus O2 2FO3 और N2O4 तो देता है 2NO2. If PCl5, PCl3 and the Cl2 are at equilibrium at the 500 K and having the concentration at 1.59 PCl3, 1.59 Cl2 and 1.41 PCl5, तो कैलकुलेट द Kc फॉर द रिएक्शन PCl5 से PCl3 प्लस Cl2 में जा रहे हैं, तो द इक्विलिब्रियम कांस्टेंट फॉर द एबव रिएक्शन कल में आ जाएगा PCl3 से Cl2 PCl5, ये आ जाएगा Kc. अगला क्वेश्चन है कि द वैल्यू of the Kc is equal to 4.24 at the 800 Kelvin for the reaction CO plus H2O, CO2 plus H2 दे रहा है. Calculate the equilibrium constant of the CO2, H2, CO and the H2 at 800 Kelvin if only CO and the H2 are present initially at the concentration of 0.10 molar each. तो CO, H2O, CO2, H2 दे रहा है, तो 1 मोलर 0.1 मोलर 0.1 मोलर 0 हो गया. तो मान लो कि 1 लीटर पर मोल है जो, तो 0.1 माइनस एक्स 0.1 माइनस एक्स तो एक्स कर देंगे. और एक्स स्क्वायर बाई 0.1 माइनस एक्स स्क्वायर इक्वल टू 4.24. इसको जब सोल्व करेंगे, ठीक है, तो x1 का वैल्यू जितना आ रहा है x2 का वैल्यू है जो इतना आ रहा है. क्लियर है. तो वैल्यू ऑफ 0.1 शुड बी नेग्लेक्टेड, इसको नेगलेक्ट कर देंगे क्योंकि इट कॉन्सेंट्रेशन ऑफ द रिएक्टेंट विच मोर देन, इससे जो रिएक्टेंट का कॉन्सेंट्रेशन है जो इनिशियल कॉन्सेंट्रेशन से ज़्यादा आ जाएगा, इसलिए इक्विलिब्रियम कॉन्सेंट्रेशन जो आएगा 0.61 और 1 माइनस 0.61 0.33 है जो ले लेंगे. तो इसमें तो ये सोल्व करना पड़ जाता है क्वाड्रेटिक, तो शायद ऐसा क्वेश्चन ऐसे आता नहीं है क्वाड्रेटिक को सोल्व करने वाला, या आता भी है तो उसमें है जो अप्रॉक्सीमेशन हम ले लेते हैं. नेक्स्ट है कि फॉर द इक्विलिब्रियम 2NO फ्यूल 2NO प्लस Cl2 द वैल्यू ऑफ द इक्विलिब्रियम कांस्टेंट Kc इज 3.15 गुना 10 के पावर -6 एट द 1069 केल्विन पर. तो कैलकुलेट द Kp फॉर द एबव रिएक्शन, तो Kp इक्वल टू आता है KcRT डेल्टा Ng. ठीक है, Kp इक्वल टू आता है KcRT डेल्टा Ng. फॉर द एबव रिएक्शन डेल्टा N निकालें तो वो आता है 1, तो Kp कितना आ जाएगा 0.033. अब बात करते हैं हेट्रोजीनियस इक्विलिब्रिया की. तो एनसीईआरटी कहता है कि इक्विलिब्रियम इज इन अ सिस्टम हैविंग मोर देन वन फेज इज कॉल्ड एज द हेट्रोजीनियस इक्विलिब्रियम. द इक्विलिब्रियम बिटवीन द वाटर वेपर एंड द लिक्विड वाटर इन ए क्लोज्ड कंटेनर इज एन एग्जांपल ऑफ द हेट्रोजीनियस इक्विलिब्रियम. H2 liquid, C2 gas जा रहे हैं. In this example, there is a gas phase and a liquid phase. In the same way, equilibrium between a solid and its saturated solution COH2 ठीक है, तो Ca2 plus 2H minus है जो दे रहा है is a heterogeneous equilibrium. Heterogeneous equilibrium often involve pure solid for the liquids. We can simplify the equilibrium expression for the heterogeneous equilibrium involving a pure liquid or the pure solid as the molar concentration of a pure solid or the liquid is a constant that means independent of the amount present. In other words, if a substance X is involved, then the X and the X solid and the X liquid are the constant, whatever the amount of the X is taken. Contrary to this, X gas and the X aqueous will vary as the amount of X in a given volume varies. Let us take the thermal dissociation of the calcium carbonate, which is an interesting and important example of the heterogeneous chemical equilibrium. तो CaCO3 को हीट करके ब्रेक कर रहे हैं CaO प्लस CO2 में. अब यहाँ पर CaCO3 भी सॉलिड है, CO भी सॉलिड है, तो इसको लेंगे ही नहीं. तो ऑन द बेसिस ऑफ द स्टोमेट्रिक इक्वेशन भी कैन राइट ये, लेकिन इसमें सॉलिड है तो ये है जो नहीं करेंगे. तो इसमें क्या आ जाएगा, तो फिर CaCO3 एंड द CO आर बोथ कॉन्स्टेंट. Therefore, the modified equilibrium constant for the thermal decomposition of the calcium carbonate will be कि K dash डायरेक्ट सिर्फ आ जाएगा पार्शियल प्रेशर ऑफ CO2 के केस में, यानी Kp इक्वल टू डायरेक्ट लिख देंगे पार्शियल प्रेशर ऑफ CO2. तो एनसीईआरटी कहता है कि दिस शो दैट एट ए पार्टिकुलर टेम्परेचर देयर इज ए कांस्टेंट कॉन्सेंट्रेशन ऑफ द प्रेशर ऑफ द CO2 इन द इक्विलिब्रियम with the COO and the CO3. Experimentally, it has been found that at 1100 Kelvin, the pressure of the CO2 in equilibrium with the CO3 and the COO is 2.0 into the square power of 5 Pascal. Therefore, the equilibrium constant at 1100 Kelvin for the above reaction is Kp equal to आता है partial pressure of CO2 equal to होता है 2.00. Similarly, in the equilibrium between the nickel carbon monoxide nickel carbonyl used in the purification of the nickel, Na plus 4CO NiCO4 है, तो Na को इग्नोर करेंगे तो द इक्विलिब्रियम कांस्टेंट इज रिटन एज NiCO4 by CO के पावर 4. तो इट मस्ट बी रिमेंबर दैट फॉर द एग्जिस्टेंस ऑफ द हेटेरोजेनियस इक्विलिब्रियम प्योर सॉलिड फॉर द लिक्विड मस्ट आल्सो बी प्रेजेंट, however a small amount may be at equilibrium, but their concentration or the partial pressure do not appear in the expression of the equilibrium constant. In this reaction, Ag2O सॉलिड प्लस 2HNO3 देता है AgNO3 प्लस H2O। तो Kc इक्वल टू आ जाएगा AgNO3 का स्क्वायर बाई HNO3 का स्क्वायर। अब यहाँ पर आ गया यूनिट्स ऑफ द इक्विलिब्रियम कांस्टेंट। तो कहता है द वैल्यू ऑफ द इक्विलिब्रियम कांस्टेंट Kc कैन बी कैलकुलेटेड बाय सब्स्टिट्यूटिंग द कॉन्सेंट्रेशन टर्म्स इन द मोल पर लीटर एंड द for the Kp partial pressure is substituted in the Pascal, kilopascal, bar or the atm. These result in the units of the equilibrium constant based on the molarity or the pressure unless the exponents of both the numerator and the denominator are same. For the reaction, H2 plus I2 2Hi, Kc and the Kp have no units. N2O4 2NO2, Kc has the unit mole per liter and the Kp has the unit bar. Equilibrium constant can also be expressed as a dimension of quantity if the standard state of the reactants and the products are specified. For a pure gas, the standard state is 1 bar. Therefore, a pressure of the 4 bar in the standard state can be expressed as the 4 bar by 1 bar यानी कि 4 which is a dimensionless number. A standard state C naught for a solute is 1 molar solution and all the concentration can be measured with respect to it. The numerical value of the equilibrium constant depends upon the standard state chosen. Thus, in this system, both Kp and the Kc are dimensionless quantities but have the different numerical values due to the different standard states. अब क्वेश्चन है कि द वैल्यू ऑफ Kp फॉर द रिएक्शन CO2 से C2CO बन रहा है तो H3 एट द 1000 केल्विन पर if initially the partial pressure of CO2 है 0.48 bar and partial pressure of CO है 0 bar and pure graphite is present, calculate equilibrium partial pressure of the CO and the CO2। तो बोलता है कि फॉर द रिएक्शन लेट x बी द डिक्रीज इन द पार्शियल प्रेशर ऑफ CO2 देन CO2 से C दे रहे हैं 2CO। तो इनिशियल प्रेशर कितना है 0.48 बार। तो 0.48 माइनस 6 और 2x आ जाएगा। तो 2x का स्क्वायर बाई 0.4 माइनस x तो कितना आ जाएगा 3। तो यहाँ से जो वैल्यू आ जाएगा x का वो आ जाएगा 0.33। तो इक्विलिब्रियम पार्शियल प्रेशर कितना हो जाएगा PuCO2 आएगा 0.66 और PuCO2 0.48 माइनस 6 यानी कि 0.15 बार है जो इसका आंसर आएगा। अब बात करते हैं एप्लीकेशन ऑफ द इक्विलिब्रियम कांस्टेंट की। तो कहता है बिफोर कंसिडरिंग द एप्लीकेशन ऑफ द इक्विलिब्रियम कांस्टेंट लेट अस समराइज द इंपॉर्टेंट फीचर ऑफ द इक्विलिब्रियम कांस्टेंट एज फॉलो। तो एक्सप्रेशन फॉर इक्विलिब्रियम कांस्टेंट is applicable only when the concentration of the reactants on the products have attained the constant value at the equilibrium state. The value of the equilibrium constant is independent of the initial concentration of the reactants on the products. Equilibrium constant is temperature dependent, having one unique value for a particular reaction represented by a balanced equation at a given temperature, or the equilibrium constant for the reverse reaction is equal to the inverse of the equilibrium constant for the forward reaction। ठीक है। नेक्स्ट है कि द इक्विलिब्रियम कांस्टेंट के फॉर ए रिएक्शन इज रिलेटेड टू द इक्विलिब्रियम कांस्टेंट फॉर द कॉरस्पॉन्डिंग रिएक्शन व्हिच इक्वेशन इज ऑब्टेन्ड बाय मल्टीप्लाइंग और डिवाइडिंग द इक्वेशन फॉर द ओरिजिनल रिएक्शन बाय अ स्मॉल इंटीजर। आगे एक लेटेस्ट कंसीडर द एप्लीकेशन ऑफ द इक्विलिब्रियम कांस्टेंट टू predict the extent of a reaction on the basis of the magnitude, predict the direction of the reaction and calculate the equilibrium concentration। अब है प्रिडिक्टिंग द एक्सटेंट ऑफ रिएक्शन। तो कहता है कि द न्यूमेरिकल वैल्यू ऑफ द इक्विलिब्रियम कांस्टेंट फॉर रिएक्शन इंडिकेट्स दैट extent of the reaction, but it is important to note that an equilibrium constant does not give any information about the rate at which the equilibrium is reached. The magnitude of the Kc or the Kp directly proportional to the concentration of the product as these appear in the numerator or the equilibrium constant expression, and inverse proportional to the concentration of the reactants these appear in the denominator. This implies that at a high value of the K is suggestive of the high concentration of the products and the vice versa. So we can make the following generalization concerning the composition of the equilibrium mixture. If Kc is greater than 10 to the power 13, product predominates over the reactants. That means if Kc is very large, the reaction proceeds nearly to the completion. Consider the following examples. दूसरा है कि द रिएक्शन ऑफ द H2 विद O2 एट 500 केल्विन हैज ए वेरी लार्ज इक्विलिब्रियम कांस्टेंट। Kc आया था 2.4 इंटू 10 का पावर 47 और H2 प्लस Cl टू 2HCl एट 300 केल्विन हैज Kc इक्वल टू 4.0 गुना 10 का पावर 31। H2 प्लस Br टू 2BHBr एट 300 केल्विन हैज Kc इक्वल टू 5.4 गुना 10 का पावर 18। If Kc less than 10 का पावर -3 तो reactant predominates over the products. That means if Kc is very small, the reaction proceeds rarely. Consider the following examples. तो the decomposition of the H2O in the H2 and the O2 at 500 Kelvin has a very small equilibrium constant Kc 4.1 गुना 10 का पावर -48 और N2 plus 4 to 2NO at 298 Kelvin has Kc 4.8 गुना 10 के पावर माइनस 31. If Kc is in the range of 10 के पावर माइनस 3 to 10 के पावर 3, appreciable concentration of both the reactants and the products are present. Consider the following examples for the reaction H2 with I2 to give the HI. Kc हो जाता है 57.0 at 500 Kelvin. Also, gas phase decomposition of the N2O4 to the NO2 is another reaction with a value of the Kc 4.6 for गुना 10 के पावर माइनस 3 at the 25 degree Celsius, which is neither too small nor too large. Hence, equilibrium mixture contains the appreciable concentration of both N2O4 and the NO2. These generalizations are listed in the table 6.6. तो रिएक्शन हार्डली प्रोसीड्स अगर कम रहेगा तो 10 के पावर माइनस 3 से 10 के पावर 3 के बीच में अगर केफी है तो बोथ रिएक्टेंट एंड प्रोडक्ट्स आर प्रेजेंट एट इक्विलिब्रियम. और बहुत ही केफी का वैल्यू लार्ज है, इसका मतलब कि सबसे ज़्यादा उसमें प्रोडक्ट है, यानी कि रिएक्शन ऑलमोस्ट कंप्लीट ही हो गया है. अब बात करते हैं प्रिडिक्टिंग द डायरेक्शन ऑफ द रिएक्शन. तो द इक्विलिब्रियम कांस्टेंट हेल्प्स इन प्रिडिक्टिंग द डायरेक्शन इन विच आर गिवन रिएक्शन विल प्रोसीड एट एनी स्टेज. For this purpose, we calculate the reaction coefficient Q. The reaction coefficient Q, Qc with the molar concentration and Qp with the partial pressure is defined in the same way as the equilibrium constant Kc, except that the concentration in the Qc are not necessarily equilibrium values. For a general reaction AABB Cc dd, Qc equal to होता है Cc dd AABB, then if Qc greater than Kc, the reaction will proceed in the backward direction. ठीक है. और इफ Qc is less than Kc, the reaction will proceed in the forward direction. अब है कि इफ Qc is equal to Kc, the reaction mixture is already at equilibrium पर होगा. और consider the gaseous reaction of the H2 with the I2. तो H2 plus I2 होता है 2HI, Kc होता है 57.0 at 500 Kelvin पर. तो suppose we have the molar concentration H2 0.1 molar, I2 0.2 and HI 0.4 molar. The subscript T on the concentration symbol means that the concentration were measured at the some arbitrary time T, not necessarily at the equilibrium. Thus, the reaction coefficient Qc at this stage of the reaction is given by इतना. Now, in this case, Qc is equal to 8.0 does not equal Kc 51.0 for the mixture H2, I2 and the HI is not at the equilibrium, then it is more H2 and I2 will react to form the more HI and their concentration will be decreased till the Qc is equal to आता है Kc. आगे है कि द रिएक्शन कोफिशिएंट Qc is useful in predicting the direction of the reaction by comparing the value of the Qc and the Kc. Thus we can make the following generalization concerning the direction of the reaction. कि अगर Qc है जो लेस देन Kc है तो फॉरवर्ड डायरेक्शन में जाएगा. Qc इक्वल टू Kc है तो रिएक्टेंट्स एंड प्रोडक्ट्स है जो इक्विलिब्रियम पर होगा. और अगर Qc ज़्यादा होगा Kc से तो रिएक्टेंट्स जो है मतलब बैकवर्ड डायरेक्शन में होगा रिएक्शन. तो इफ़ Qc लेस देन Kc है तो है जो फॉरवर्ड डायरेक्शन में आएगा. इफ़ Qc ग्रेटर देन Kc है तो बैकवर्ड डायरेक्शन में जाएगा. और Qc इक्वल टू Kc है तो इक्विलिब्रियम पर होगा. नो नेट रिएक्शन ऑकर्स. Therefore, the value of Kc for the reaction 2FB plus C2 into 10 to the power minus 3 at a given time. The composition of the reaction mixture A, B, C equal at 3 गुना 10 के पावर माइनस 4 मोलर. तो इन बिट डायरेक्शन द रिएक्शन विल प्रोसीड. तो Qc निकालेंगे B से C एक स्क्वायर, ए बी सी इक्वल है तो 3 गुना 10 के पावर माइनस 4 यानी कि 1 आ रहा है. तो Qc बड़ा है Kc से, इसका मतलब कि रिएक्शन जो जाएगा वो जाएगा रिवर्स डायरेक्शन में. अब देखते हैं कैलकुलेटिंग द इक्विलिब्रियम कॉन्सेंट्रेशन को कैसे कैलकुलेट करेंगे. तो इन द केस ऑफ द प्रॉब्लम इन विच वी नो द इनिशियल कॉन्सेंट्रेशन बट डू नॉट नो एनी ऑफ द इक्विलिब्रियम कॉन्सेंट्रेशन, द फॉलोइंग 3 स्टेप्स शॉल बी फॉलोड. Step 1, write the balance equation for the reaction. Step 2, under the balance equation, make a table that lists for each substance involved in the reaction or the initial concentration, the change in the concentration on going to the equilibrium, and the equilibrium concentration. In constructing the table, define X as the concentration mole per liter of one of the substance that reaction going to the equilibrium. Then use the stoichiometry of the reaction to determine the concentration of the other substances in the terms of the X. Step 3 है कि substitute the equilibrium concentration into the equilibrium equation for the reaction and solve for X. If we are to solve a quadratic equation, choose the mathematical solution that makes chemical sense. और स्टेप 4 है कि कैलकुलेट the equilibrium concentration from the calculated value of the X. और स्टेप 5 है कि check your yield by substituting them into the equilibrium equation. क्वेश्चन नेक्स्ट है कि 13.8 ग्राम ऑफ द N2O4 by placed in a 1 liter reaction vessel at 400 Kelvin and allowed to attain equilibrium N2O4 फिर 2 NO है जो 2 बन रहा है. The total pressure at equilibrium was found to be 9.15 bar. To calculate the Kc, Kp and the partial pressure at equilibrium. तो हम जानते हैं PV इक्वल टू क्या होता है. PV इक्वल टू होता है NRT. वॉल्यूम हो गया 1 लीटर. मॉलिक्यूलर मास N2O4 का होता है 92 ग्राम. नंबर ऑफ द मोल्स होता है 13.8 बाई 92 यानी 0.15. गैस कांस्टेंट दिया होता है 0.083. टेम्परेचर दिया हुआ है 400 केल्विन. तो यहाँ पे प्रेशर निकालेंगे PV बराबर NFT से तो 4.98 आ जाएगा. अब N2O4 फिर 2NO2 जा रहा है तो 4.98 माइनस एक्स और 2x हो जाएगा एट इक्विलिब्रियम पर. तो P टोटल एट इक्विलिब्रियम पर कितना है 4.98. P टोटल है 9.15 क्वेश्चन में दिए हुए. तो 9.15 इज इक्वल टू 4.98 प्लस 2x. तो यहाँ से x आ जाएगा 4.17. तो पार्शियल प्रेशर एट इक्विलिब्रियम कितना हो जाएगा. P N2O4 का आ जाएगा 0.81 बार और PnO2 का आ जाएगा 8.34 बार. Kp कितना आ जाएगा 85.87 और Kp इक्वल टू होता है Kc RT डेल्टा Ng. ठीक है. तो यहाँ से KT निकल जाएगा 2.6 आ जाएगा. Kp निकाल लिए थे. Kp से फिर Kc निकाल सकते हैं. अगला क्वेश्चन है कि 3 मोल ऑफ द PCl5 kept in the 1 liter closed container vessel was allowed to attain the equilibrium at 380 Kelvin. तो कैलकुलेट द कंपोजिशन ऑफ द मिक्सर एट द इक्विलिब्रियम. Kc दिया हुआ 1.8. तो PCl5 से PCl3 Cl2 जा रहे हैं. 3 हो गया 0 0. तो लेट x मोल पर लीटर ऑफ द PCl5 बी डिसोसिएटेड एट इक्विलिब्रियम. तो 3 माइनस एक्स और एक फॉर एक्स हो गया. तो 1.8 इजिकल टू एक्स स्क्वायर बाई 3 माइनस एक्स. अब इसको क्वाड्रेटिक को सोल्व करेंगे तो वैल्यू आ जाता है. ठीक है 1.59. ठीक है आ रहा है वैल्यू. तो PCl5 हो जाएगा 1.41. 3 माइनस 1.59 और PCl3 इजिकल टू Cl2 इजिकल टू हो जाएगा 1.59 मोलर. अब देखते हैं रिलेशन बिटवीन द इक्विलिब्रियम कांस्टेंट K, रिएक्शन कोफिशिएंट Q एंड द गिब्स एनर्जी G. तो the value of the Kc for the reaction does not depend on the rate of the reaction. However, as you have studied in the unit 5, it is directly related to the thermodynamics of the reaction and in particular to the change in the Gibbs energy delta G. If delta G is negative, then the reaction is spontaneous and the proceeds in the forward direction. If delta G is positive, then the reaction is considered non-spontaneous. Instead, as reverse reaction would have a negative delta G, the products of the forward reaction shall be converted to the reactants. Or delta G is 0, the reaction has achieved equilibrium at this point. There is no longer any free energy left to drive the reaction. So mathematical expression for this thermodynamic view of the equilibrium can be described by the following equation. कि delta G इक्वल टू होता है delta G नॉट प्लस RT ln Q, बेयर delta G नॉट क्या है तो स्टैंडर्ड गिब्स एनर्जी है. एट इक्विलिब्रियम व्हेन द delta G बराबर 0 and Q इक्वल टू QC, the equation 6.21 becomes delta G equal to delta G naught plus RT ln K. तो delta G naught इक्वल टू आ जाएगा माइनस RT ln K. तो ln K इक्वल टू आ जाएगा माइनस डेल्टा एल जी बाई RT. अब कहता है टेकिंग द एंटी लॉग ऑन बोथ साइड वी गेट K इक्वल टू ई के पावर माइनस डेल्टा G बाई RT. तो हेंस यूजिंग द इक्वेशन 6.23 the reaction spontaneity can be interpreted in the terms of the value of the delta G naught. If delta G naught less than 0, then the minus delta G naught by RT is positive and the e के power minus delta G by RT greater than 1 making K greater than 1, which implies a spontaneous reaction or the reaction which proceeds in the forward direction to such extent that the products are present predominantly. If delta G naught greater than 0, then the delta minus delta G naught by RT is negative and e के power minus delta G naught by RT is less than 1, that is K is less than 1, which implies that non-spontaneous reaction or a reaction which proceeds in the forward direction to such a small degree that only a very minute quantity of the product is formed. अब क्वेश्चन है कि द वैल्यू ऑफ द डेल्टा जी फॉर द फॉस्फोरिलेशन ऑफ द ग्लूकोज इन द ग्लाइकोलिसिस इज 13.8 किलोजूल पर मोल. तो फाइंड द वैल्यू ऑफ द Kc एट 298 केल्विन. तो डेल्टा जी इक्वल टू 13.8 किलोजूल पर मोल यानी 13.8 गुना 10 के पावर 3 जूल पर मोल. तो अल्फा डेल्टा जी नॉट इक्वल टू आ जाएगा माइनस RT ln Kc. तो ln Kc इक्वल टू ठीक है इतना आ जाएगा. तो Kc इक्वल टू इतना यानी इसको तो बस कैलकुलेटर से निकाल सकते हैं. तो ये आंसर आ जाएगा. हाइड्रोलाइसिस ऑफ द शुगर गिव्स सुक्रोज. हाइड्रोलाइसिस ऑफ शुगर कुछ इस प्रकार से होता है कि सुक्रोज प्लस H2O ग्लूकोज प्लस फ्रुक्टोज देता है. इक्विलिब्रियम कांस्टेंट Kc फॉर द रिएक्शन इज 2 × 10⁻13 एट 1300 केल्विन. द कैलकुलेट द डेल्टा G नॉट एट 1300 केल्विन. तो डेल्टा G नॉट इक्वल टू आता है माइनस RT ln Kc. डेल्टा G नॉट माइनस आठ आठ का वैल्यू रखेंगे -81314 गुना मोल गुना 300 गुना ln 2 के पावर 10 के 13, तो डेल्टा जी आ जाएगा -1.64 गुना 10 के पावर 4 जूल पर मोल। अब है फैक्टर्स अफेक्टिंग इक्विलिब्रियम, तो कहता है वन ऑफ द प्रिंसिपल गोल्स ऑफ द केमिकल सिंथेसिस इज टू मैक्सिमाइज द कन्वर्जन ऑफ द reactants to products while minimizing the expenditure of the energy. This implies the maximum yields of the products at the mild temperature and pressure condition. If it does not happen, then the experimental condition need to be adjusted. For example, in the Haver's process for the synthesis of the ammonia from the N2 and the H2, the choice of the experimental condition is of the real economic importance. Annual world production of the ammonia is about 100 million tons, primarily for the use as the fertilizers. Equilibrium constant Kf is independent of the initial concentration, but if a system at equilibrium is subjected to a change in the concentration of one or more of the reacting substances, then the system is no longer at equilibrium, and the net reaction takes place in the some direction until the system returns to the equilibrium once again. Similarly, a change in the temperature or the pressure of the system may also alter the equilibrium. In order to decide what course the reaction adopts and make a quantitative prediction about the effect of a change in the condition on equilibrium be used Lee-Chatelier principle. It states that a change in any one of the factors that determine the equilibrium condition of a system will cause the system to change in such a manner so as to reduce or to contract the effect of the change. This is applicable to all the physical and the chemical equilibria. Before not discussing the factors which can influence the equilibrium. तो कहता है कि इफेक्ट्स ऑफ द कॉन्सेंट्रेशन चेंज, तो कहता है इन जनरल व्हेन द इक्विलिब्रियम इज disturbed by the addition or removal of any reactant or products, Lee-Chatelier principle predicts that the concentration of stress of an added reactant or product is relieved by a net reaction in the direction that consumes the added substance, or the concentration of stress of a removed reactant or product is relieved by the net reaction in the direction of the replenished that removed the substance. In other words, when the concentration of any one of the reactants or the products in a reaction at equilibrium is changed, the composition of the equilibrium mixture changes so as to minimize the effect of the concentration change. Let us take the reaction H2 plus I2 2HI. If H2 is added to the reaction mixture at the equilibrium, then the equilibrium of the reaction is disturbed. In order to restore the reaction proceeds in the direction wherein H2 is consumed. That means more H2 and the I2 reacts to form the HI, and finally the equilibrium shifts in the right forward direction. This is in the accordance with the Lee-Chatelier principle, which implies that in the case of the addition of reactants or products, a new equilibrium will be set up in which the concentration of the reactant or product should be less than what it by after the addition but more than what it by left in the original mixture. तो यहाँ पर दिया हुआ है इफेक्ट ऑफ द एडिशन ऑफ द H2 ऑन द चेंज ऑफ द concentration of the reactant and the products in the reaction H2 plus I2 2HI. The same point can be explained in the terms of the reaction coefficient QC. तो QC इक्वल टू आया था HI के स्क्वायर बाई H2 I2. तो कहता है कि एडिशन ऑफ द हाइड्रोजन एट इक्विलिब्रियम रिजल्ट्स इन द वैल्यूज ऑफ द क्यूसी बीइंग लेस देन Kc. Thus, in order to attain the equilibrium, again reaction moves in the forward direction. Similarly, we can say that removal of a product also boosts the forward reaction and increase the concentration of the products and the has greater commercial application in the case of the reactants, where the product is a gas or a volatile substance. In the case of the manufacture of the ammonia, ammonia is liquefied and removed from the reaction mixture so that the reaction keeps moving in the forward direction. Similarly, in the large-scale production of the CO used as the important building material from the CO3, constant removal of the CO2 from the kiln drives the reaction to the completion. It should be remembered that the continuous removal of a product maintains QC at a value less than Kc and the reaction continues to move in the forward direction. अब बात करते हैं इफेक्ट ऑफ द कॉन्सेंट्रेशन एंड एक्सपेरिमेंट. तो कहता है कि दिस कैन बी डेमोन्स्ट्रेटेड बाय द फॉलोइंग रिएक्शन Fe3 प्लस FCN माइनस FCN माइनस होता है कलरलेस देता है FeFCN जो कि होता है डीप रेड. तो रेडिश कलर्ड appears on adding 2 drops of the 0.022 m potassium thiocyanate solution to the 1 ml of 0.2 m iron 3 nitrate solution due to the formation of the FeFCN2 plus. The intensity of the red color becomes constant on attaining equilibrium. This equilibrium can be shifted in either forward or the reverse direction depending upon the choice of adding a reactant or a product. The equilibrium can be shifted in the opposite direction by adding the reagents that remove the Fe3 plus or the Fe minus ions. For example, oxalic acid H2C2O4 reacts with Fe3 plus ions to form the stable complex ion FeC2O4 3K3 minus, thus decreasing the concentration of the free Fe3 plus ion. In accordance with the Lee-Chatelier principle, the concentration of stress of the room weight Fe3 plus is relieved by dissociation of the FeFn2 plus to replenish the Fe3 plus ion, because the concentration of the FeFn2 plus decreases, the intensity of the red color decreases. Addition of the aqueous AgCl2 also decreases the red color because Ag2 plus reacts with the Fn minus ion to form the stable complex ion AgFn4 2 minus. Removal of the free Fn aqua shifts the equilibrium in the equation from the right to left to replace the Fn minus ion. Addition of the potassium thiophanate on the other hand increase the color intensity of the solution as it shifts the equilibrium to the right. अब बात करते हैं इफेक्ट ऑफ द प्रेशर चेंज की. तो a pressure change obtained by changing the volume can affect the yield of the products in the case of the gaseous reaction, where the total number of the moles of the gaseous reactant and the total number of the moles of the gaseous products are different. In applying the Lee-Chatelier principle to a heterogeneous equilibrium, the effect of the pressure change on the solids and the liquids can be ignored because the volume and the concentration of the solution liquid is nearly independent of the pressure. To consider the reaction CO plus 3H2, CH4 plus H2O. Here 4 mole of the gaseous reactant CO plus 3H2 becomes 2 mole of the gaseous product CH4 plus H2O. Suppose the equilibrium mixture for the above reaction kept in a cylinder fitted with a piston at a constant temperature compressed to 1/2 of its original volume. Then the total pressure will be doubled according to the PV Bravo constant. The partial pressure and therefore the concentration of the reactant and the products have changed and the mixture is no longer at equilibrium. Direction in which the reaction goes to re-establish the equilibrium can be predicted by applying the Lee-Chatelier's principle. Since pressure has doubled, the equilibrium now shifts in the forward direction. A direction means the number of the moles of the gas or the pressure decreases. We know pressure is proportional to the moles of the gas. This can be understood by using the reaction coefficient Qc. Let CO, H2, CH4 and the H2O be the molar concentration at equilibrium for the methanation reaction. When the volume of the reaction mixture is halved, the partial pressure and the concentration are doubled. We obtain the reaction coefficient by replacing the equilibrium concentration by doubling its value. So as Qc less than Kc, the reaction proceeds in the forward direction. In the reaction C plus CO2 to CO, when the pressure increases, the reaction goes in the reverse direction because the number of the moles of the gas increase in the forward direction. अब effect of the inert gas addition. If the volume is kept constant and an inert gas such as the argon is added which does not take part in the reaction, the equilibrium remains undisturbed. It is because the addition of an inert gas at the constant volume does not change the partial pressure or the molar concentration of the substance involved in the reaction. The reaction coefficient changes only if the added gas is a reactant or the product involved in the reaction. फिर बात करते हैं इफेक्ट ऑफ द टेम्परेचर चेंज की. तो वेन एवर एन इक्विलिब्रियम इज डिस्टर्बेड by a change in the concentration, pressure or the volume, the composition of the equilibrium mixture changes because the reaction coefficient Qc no longer equals the equilibrium constant Kc. However, when a change in the temperature occurs, the value of the equilibrium constant Kc is changed. In general, the temperature dependence on the equilibrium constant depends on the sign of the delta H for the reaction. The equilibrium constant for an exothermic reaction negative delta H decreases as the temperature increases, or the equilibrium constant for an endothermic reaction positive delta H increases as the temperature increases. Temperature change affect the equilibrium constant and the rate of the reaction. फिर production of the ammonia according to the reaction N2 plus 3H2 NH2NH3 in exothermic process according to the Lee-Chatelier principle, raising the temperature shift the equilibrium to the left and decrease the equilibrium concentration of the ammonia. In other words, low temperature is favorable for the high yield of the ammonia, but practically very low temperature slow down the reaction and thus a catalyst is used. अब बात करते हैं इफेक्ट ऑफ द टेम्परेचर एंड एक्सपेरिमेंट. तो इफेक्ट ऑफ द टेम्परेचर ऑन द इक्विलिब्रियम कैन बी डेमोन्स्ट्रेटेड बाय टेकिंग द NO2 गैस, ब्राउन गैस जो कि होता है इन द कलर, विच डायमराइज इनटू N2O4 गैस जो कि होता है कलरलेस. यानी NO2 है ब्राउन पर N2O4 जो कि NO2 का डायमराइज से बना है वो होता है कलरलेस. तो 2NO2 डैमराइज होकर N2O4 बना दिया और ये एक्सोथर्मिक रिएक्शन है. तो NO2 gas prepared by the addition of the fuel turning to the concentrated NO3 is collected in the 2 ml to 5 ml test tube, ensuring same intensity of the color of the gas in the each tube, and a stopper filled with the ठीक है 3 high ml beakers 1, 2 and 3 containing the freezing mixture water at the room temperature and hot water 363 Kelvin respectively are taken. Both the test tube are placed in the beaker 2 for the 8 to 10 minutes. After this one is placed in the beaker 1 and the other in the beaker 3. The effect of the temperature on the direction of the reaction is depicted very well in this experiment. At the low temperature in the beaker 1, the forward reaction of the formation of the N2O4 is preferred, and the reaction is exothermic, and thus the intensity of the brown color due to the N2O4 decreases. While in the beaker 3, high temperature favors the reverse reaction of the formation of the N2O2 and thus the brown color intensifies. Effect of the temperature can also be seen in the endothermic reaction. जैसे CO H2O जो होता है वो पिंक होता है और 4Cl माइनस कलरलेस होता है तो CuCl4 माइनस बनाएगा जो कि होता है ब्लू. तो एट द रूम टेम्परेचर द इक्विलिब्रियम मिक्सचर इज ब्लू कलर ड्यू टू द CuCl4 माइनस व्हेन कूल्ड इन अ फ्रीजिंग मिक्सचर द कलर ऑफ द मिक्सचर टर्न्स पिंक ड्यू टू द CuH2O6 3+. अब बात करते हैं इफेक्ट ऑफ ए कैटालिस्ट की. तो कैटालिस्ट इंक्रीज द रेट ऑफ ए केमिकल रिएक्शन बाय मेकिंग अवेलेबल अ न्यू लो एनर्जी पाथवे फॉर द कन्वर्जन ऑफ द रिएक्टेंट टू प्रोडक्ट्स. It increase the rate of the forward and the reverse reaction that pass through the same transition of state and do not affect the equilibrium. Catalysts lower the activation energy for the forward and the reverse reaction by reacting the same amount. Catalysts do not affect the equilibrium composition of the reaction mixture. Do not appear in the balanced chemical equation or in the equilibrium constant expression. Catalysts consider the formation of the NH3 from the dinitrogen and the dihydrogen, which is highly exothermic reaction and proceeds with the decrease in the total number of the moles formed as compared to the reactants. Equilibrium constant decreases with increase in the temperature. At low temperature, rate decreases and it takes long time to reach at equilibrium, whereas high temperature gives satisfactory rates but poor yields. ठीक है. तो Haber discovered that a catalyst consisting of the iron catalyst the reaction to occur at a satisfactory rate at temperatures where the equilibrium concentration of the Na3 is reasonably favorable. Since the number of the moles formed in the reaction is less than the number of those of the reactants, the yield of Na3 can be improved by increasing the pressure. Optimum condition of the temperature and the pressure for the synthesis of the Na3 using the catalyst are around 5000 degrees Celsius and 200 atm. Similarly, in the manufacture of the sulfuric acid by the contact process, 2FO2 plus O2 2FO3 Kf equal to 1.7 गुना 10 के power 26. Though the value of the K is suggestive of the reaction going to the completion, but practically the oxidation of the FO2 to FO3 is very low. Thus, the platinum or the divanadium pentoxide V2O5 is used as the catalyst to increase the rate of the reaction. Note that if a reaction has an exceedingly small K, a catalyst would be of little help. तो यहाँ पर हो जो केमिकल इक्विलिब्रियम कंप्लीट होता है. ठीक है, केमिकल इक्विलिब्रियम यहाँ पर है जो कंप्लीट है.